So let's get started. We are recording. Good to go. I promised there wouldn't be any more slides, but I lied. There's just really quickly we're going to do a couple of things going over the final project. Okay, so yeah, now is the time to just maybe start thinking about this a little bit. So the project is really kind of an opportunity to both apply what you've learned, but also to apply it to things that you guys actually are interested in, want to do research in. So I will mention that a lot of the research projects that come out of this class, or some of them, people have gone on to publish in papers or use as part of their thesis or dissertation. So I actually highly encourage that. I want this to be kind of as useful as possible to everyone. And I'll also mention, this is not like an individual project, so you can if you want, but you're also welcome to work in groups of, how many people are in the class? Does anyone know? Let's say up to 3 people, okay? Yeah, because I have to balance the presentations at the end of class and how much time we have. So we'll say between 1 to 3 people for the projects. So all of this information is on Canvas if you haven't already seen it before. In the files, there is a final project folder that contains basically all the information that you need to know about each of the deliverables for the project. So this constitutes, the 3 of these together constitute some portion of your grade, with the report being the most important, then the presentation, and then the proposal. Due dates are here, so you have on the order of a couple weeks for the proposal, and then the presentation is due on the start of the class that you guys present, and then the project report is due at the end of finals week. Okay? And then, like I said, the rubric for each of these parts is available on Canvas, so you'll know kind of what I'm looking for and what I'm grading for. So for each of the components of the project, the proposal, the reason why I set it up this way is basically to get people thinking about their project a little bit earlier on, so that you're not doing everything sort of last minute. I'll note that the proposal that you submit isn't like totally tie you down to whatever you've proposed. If you've been doing a lot of work and you feel like it's just not the right direction, the data set's not good, then you are welcome to change your proposal your project topic. It'd probably be best to come talk to me and Lou about that. So here we do want to understand a little bit about the data set so I can help scope the project appropriately. I might say this data set is way too small and narrow for the purposes of what I expect you to be doing, or I could say this is going to be way more than you do over the course of a quarter, and so this is just to help with scoping as well. For the presentation, 10 to 15 minute presentation, and again, all of this information available on Canvas. And the project report, people always ask me about page length. I don't really care about page length. The focus is more on the content. And I also want to understand a little bit about the process that you've taken as a data analysis. It's not just about, I took this data and then I used this particular model and then here's the results. Hopefully you guys are getting a sense of that in this class. We really want to be holistic in the way we're thinking about doing data analysis, and so the report should reflect that. Any questions about project report? Yeah.
I was wondering if you might be able to make like an example available on the
I'll do that. I'll post like 3 or 4 projects that people have done in the past. Yeah. Yes?
For topic, do you want it to be specifically focused in transportation?
No. It can be anything. Okay. Like I said, I want it to be something that you are interested in, and then hopefully something that can be useful for your current or future research, right? Yeah. I know this is like a TTP class, but like, it's not really. Yeah.
I saw earlier in the presentation, I saw something regarding regression.
Yes.
So the project will need to be something involving regression.
Yeah, it's a data analysis class, so that means we're doing regressions. Yeah. Yeah.
If we cover more deep concept, for example.
Yeah. So,
Or should just cover the concept that we learned.
yeah, no, it doesn't have to be, and so some people have, so it's a little tricky, right? Because you're gonna be doing this project at the same time that you're learning some of this material, and so maybe you want to apply stuff that we're gonna be learning kind of at the end, and so that may require you to do some independent learning. Maybe you have some expertise in some data analysis methods already. And hopefully some of what you're learning here can complement that, and you can show that in the report. But yeah, people have done all sorts of things. I think last year there was a group that did a whole bunch of CNN image analysis stuff that we like we cover at a very high level in this class, but that's totally fine, right? And so really I want this to be useful for you. Yeah, if you're not sure about it, come talk to me, and I'm happy to help hash it out. Okay, any other questions? All right, great. So, okay. So I'm just gonna say this once because I actually have been getting a few emails. So as far as homework extensions, my policy is unless there's a valid medical reason, I don't really provide extensions. So you guys will have to kind of figure out how to balance, taking more time to do the homework versus the late grade penalty. It's like 5% a day, so it's not too crazy, right? So I'll let you guys kind of figure that out on your own. But really, there aren't any going to be extensions to the homework due dates. Okay. Okay, so we'll start off with notes. Switch screens. Okay. So, lecture 6. Actually, before I jump into the lecture 6 material, I know that I kind of scrambled at the end last time to cover everything. Are there any questions left over from last time that anyone would like me to cover? Okay. In which case, we will continue on. So today we're gonna try and hone in a little bit on some of the concepts that I was talking about as it regards to fits of our models against data and against like test data. So let's look at our same thing again, just as a refresher. We've got a couple of data points like this. I may have a line that goes through here. And we talked about how you could have other sort of fits that go through the data that might actually do better than a linear model. And so we're going to kind of look at that in more detail today. So one way that I want to kind of explore this concept is thinking about how we can create a better fit by adding more explanatory variables. And one of the ways you can do that is, well, this can essentially help change the functional form. And so one of the ways that I can think about doing this is, let's do something like this. So y equals beta 1 x, and from here I can maybe do something like y equals beta 1 x plus beta 2 x squared. And what that does is you're essentially introducing degrees of freedom. And so my curve may end up getting like a little bit squigglier, right, as I add an additional explanatory variable. And I can continue to do this as a way to introduce more squiggliness to the line in order to better fit my model to the data, right? But as we discussed before, if I'm using a true function to generate these points, and I add more points based off of the true function, so if I generate more points, suddenly the model is bad. Okay, so this is a concept that I've been kind of going back to a bunch of times, right? And so right now the goal is to try and formalize this sort of idea and what's happening here. Okay, so the concept is that I can add more complexity to the model, and that lets me get closer to my points, right? But at a certain point, if I add too much complexity to the model, then my ability to do predictions on, let's say, this other set of data start to diminish. Yeah?
When you're saying that we can create a better fit by adding more explanatory variables, are the explanatory variables the beta? Beta 1, beta 2?
Yes. No, sorry. Those are the parameters connected to our explanatory variables. The explanatory variables in this particular case would be x, x squared, x cubed, x to the fourth, and so on. Okay.
Are they really different?
Yes, they would be, right? Because so the way that you can think about this is a column of numbers. This is a different column of numbers. This is another different column of numbers. And then you are introducing degrees of freedom. And I'm going to show you that if you do this, it will do something like this. Okay, so I'll show you that in a second. But the bigger takeaway is adding complexity to the model to allow for better fit. So as you add more variables, you will always have a better fit, right? Because at the very least, I could always make this be 0 and it would be the same as before, right? So it will always perform at least as good as a model with fewer variables. And what we're trying to balance here is doing too much complexity. Okay. So that leads us to talking about this trade-off. And so formally, we call this a bias variance trade-off. So what is bias and what is variance? Okay, I'm going to do a pretty simple example here. I'm going to draw 4 target areas. And imagine that you are throwing darts at this target. And if you manage to hit all of your darts in a tight cluster right at the center, then we consider this to be low variance as well as low bias. Okay? What about if I had low variance but high bias? Then I might look something like this. So the idea here is bias refers to how kind of centered the data is. And so if you think about a ground truth about where data is functionally located, what values those might be, if all of my predictions are not close to or are not centered around that truth, then I have higher bias, right? And so so bias is like, especially if you are kind of on one side. And variance is in reference to kind of the spread, right? And so if I had low bias but high variance, then my predictions would be centered around that truth value, but I might be spread out quite a bit, right? And then if I had both high variance and high bias, then I might be both spread out and also not centered. Okay? Any questions about that? Okay, so when we talk about error, I'm going to write out the sort of formal statistical equation for what constitutes an error. And it looks something like this. And I can take this equation and expand it out, and it would end up looking something like this.
Is that f hat or the derivative of that?
F hat. Squared. Okay, so like I said, this is not a theory class where we're deriving any of this stuff. And the reason, I'm missing am I missing? No, that's right. The reason why I'm showing this is actually, this is the formalized sort of definition for error, which is broken down into 3 components. Okay, Does anyone know what the components happen to be? So this is bias squared plus variance plus noise. Okay. So the components of your total error are equal to the sum of your bias, variance, and noise. Noise is kind of random, so we can kind of disregard this in the sense that we don't expect noise to be correlated with choice of model, right? But our choice of model can have an impact on the bias and variance. And there is this kind of fundamental relationship, which I've been talking about, and that looks something like this. So if our error is on the y-axis and the model complexity is on the x-axis, then bias decreases, right, as you have more and more model complexity. Okay? But your variance will increase with model complexity. And our total error looks something like this, the sum of these two. And so really what we're aiming for here is to define the balanced model complexity that has the optimal bias variance trade-off so that you are at the lowest point in your total error. Okay? And to demonstrate what this means in kind of our original example, right? So with regards to how close a line is to the original black points, which one is the closest? The black, the red, or the blue? The blue. So getting close to those points is all about decreasing bias, okay? And then when I think about the spread of data as it relates to each of these models, right, you can see that as I make the line more squiggly, and you can think of it even as more extreme going up and down, the distance of, let's say, the green points from my model fit starts to increase, right? And that's the variance component, okay? So we want to figure out essentially the best squiggliness of the line to get to in order to be at our optimal error. We want to be at the lowest point of the total error. Okay? Yes?
Can you remind me what the relationship of the green points to the black points is?
Yes. So the idea is like, the general idea is I can fit a model to some data, okay? And I can sort of arbitrarily make the model complex enough that I can get really, really close to that data. But how useful is that model if I'm trying to use that model to predict on new data and it's giving me totally trash results, right? And so the idea is when you train the model, we would like to leave some data out to validate predictions. And so that's the point of the green data. You can think of it as I have a function that produces these data points, that's our true function. And so I've generated a couple of points, and that would be the black data, and that's what I use to train the model on. And then I've generated new data, which would be the green points that I want to test my model against. Yeah. Yeah.
So just in terms of how you phrase these things, it's what has the variance? Is it the model which has high variance, or is it, because it seems like it's like the data that has high variance?
No, so it is in reference to the model, right? Because when you talk about error, you're talking about in reference to something. So the model itself has the error.
So it has a high variance because it's too particular to that set of data, and so it
Yep.
has high variance because it can't match itself to other.
Yeah, essentially that's what it means, yeah.
Could this be thought of as like a sample versus a population? Or are those just inappropriate terms?
It wouldn't quite be like that, yeah. I mean, in these cases, it's more accurate to describe it as, in this particular context, we're kind of describing it as like a training set and a testing set. And that's in reference to the data that's being used to train and to test the model. Now that could be coming from a sample of data, that could be coming from an entire population of data, but the treatment of it we'll think of formally as testing and training data.
Okay.
Yep. Okay. So let's take a look at an example here. So okay, I'm going to do something right now which we're not gonna, you guys don't need to follow along in coding. I'm copying and pasting a lot of code. Well, not that much, but I will walk through this so we all kind of understand what's going on. So, and this code will be available right online. I'll still post this. Okay. So I'm generating some data here, kind of similar to what we've been doing, but in this case, it's going to look a little bit different. Yeah, so this is using some like sine cosine stuff. So you have some like periodic things. I'm using. I want to make an example with pretty nonlinear data, and then we'll think about trying to fit stuff here. So this is kind of like what the data will look like that we're fitting against. And actually, this particular example that I'm showing is going to be doing kind of exactly what I was saying in the handwritten notes, where I'm going to do a whole bunch of model comparisons and building up model complexity. And the way that I'm doing that is doing x and then x plus x squared, and then x plus x squared plus x cubed. And so that's what this code is doing. So here, let's see, okay. So this is going to create a data frame where I'm just doing, each column is x to the n power, starting with 1, so it'll be x, x squared, x cubed, and so on and so forth. So we can see quite literally, where are we? Yeah, here. So I have all of my x to the various powers all the way up to x25. Okay? Oops. And then I'm going to do predictions using the model, and this is just to generate those predictions so I can draw what the model fit line looks like. So here, and then I'll talk about this stuff a little bit later. Yeah, I'll talk about this in a second. Okay. One second, let me make sure. One sec. Which one is being printed? Label geom test. Okay. Okay, so what's going on here? So ignore the blue points, ignore this number that's being printed here. Just focus on the red line and the black points, okay? So the black points are the same for every single one of these. And right at the very first one, we have a set of data points, and I am running a linear regression of y on x. And that red line goes through those points, and you can see, right, okay, there's some fit there, and then I can figure out what the error is. So does anyone remember how we calculate the average error, or the mean squared error? Yeah.
We go through each data point, compare it to where the line would place it.
Uh-huh.
The difference, square that, do that for every data point.
Yep.
And average all that.
Exactly, right? And so it's red line, distance to each black point, square that, and then take the average, okay? And so that's telling us, it's kind of like how, on average, how far the black dots are away from the red line. Okay, so that is how you would calculate your mean squared error. And number two, we are adding a degree of freedom. This fit is not only beta x, but plus beta x squared, right? So number two has x and x squared. And now you can see it's not just a flat straight line, it's actually a quadratic line. And this is the best fit with the quadratic line. And so what do you guys think? If I were to do the mean squared error of number two compared to number one, would number two have a lower or higher mean squared error? Lower, right? And in fact, can I print out those errors? I thought at some point that it was supposed to print that out, but not here, and I don't want to do it on the fly. So I will just ask you to trust me that if you calculate the MSE, for the red line fit against the black dot points, you will see that the mean squared error will continue to decrease as I add more and more variables. And that is a universal fact, right? And that has to do with the fact that I am decreasing the bias as I go through all of these guys. Okay, and as we progress on, same type of thing, I am adding more degrees of freedom, more wiggle room for the red line to kind of match the black data points, right? And so you can see by 7 or 8, actually that waveform function is actually being replicated fairly decently by the fact that I'm increasing the model complexity. Okay. And you even start to get, it might be a little bit hard to see, but when you, especially when you have higher density of points, like the line may actually swiggle a lot more when I'm getting to these more extreme numbers of variables that I'm adding into the model. Okay. And again, calculating MSE, the lowest MSE that you'll find is 25 when I have the most variables in here. Okay, but like I said, we have this intuition that increasing complexity may not make the model actually better, especially when we're thinking about, right, predicting to values that the model wasn't initially trained on. And so that's actually what's happening here. The blue dots are the test set. And so I've used actually the same function, but different random numbers to generate these blue points. Okay. And now I can do what's called an out of sample mean squared error, which means I am now, instead of comparing the red line against the black dots, which I trained the model on, I can now compare the red line against the blue dots, which is the same functional form of the original data, but it's a different data set. Okay? And so when I do that, now I have a glimpse into the variance component of the error, and I can have, I can calculate the total error based off of the out of sample mean squared error. And that's what this number is in the middle, right? And so what does the shape of the total error look like as a function of model complexity? It goes like down, then up, right? And so 1 going down, it's not always like perfectly like this, right? Because you actually have some variability in the error as kind of a function of the fact that this stuff is this stuff has the noise component, right? Which can influence the size of the error. That's the third component that we don't really have control over. So you won't always get this perfect shape like this. But generally you'll see that the out of sample mean squared error goes down, and then it will come back up. The noise in this one is particularly bad. I probably should do a better example, but you can see what's our lowest one is probably like 0.6 around here. And so around here maybe is where you would have your best model fits to be able to predict things outside of the original sample. And then it gets bad again. And then randomly good again down there. But yeah.
So the out of sample, what was it you said, out of sample?
Mean squared error.
Mean squared error, that would be an indicator of variance?
No, that's our indicator for our total error, which includes the variance term, but also includes the bias term.
Okay.
Really, I'm juggling between being informal about it, but then being a little too formal. But the intuition, right, is that you have a model, you train the model on data, and you want to be able to get good predictions from the model, right? If you just predict stuff from the data that you trained the model on, like how good are those predictions? Well, I can artificially make them good because I trained my model on them. But really, a probably better indicator of how good the model is if I were able to take a different data set that I didn't train the model on and it still gives me good predictions, right? So that's what we're fundamentally doing here. And the formalization of this and the reasoning behind why a certain choice of model is good has to do with the like statistical background, right? The fact that you have these variance or bias variance trade-offs, and you know, to perform that thing where I get the best model for out of sample mean squared error, you are having to essentially look at a bunch of different models and then test them and figure out which one has the lowest, essentially. Yeah.
The mean squared error is, it doesn't have a range, right? It just starts at 0 and can go up forever. It's not from 0 to 1.
Yeah, that's right. Yeah, and so unlike a R squared, this isn't like a thing that you can easily compare between different things that are generating mean squared errors. But in this case, we are comparing mean squared errors, and we're able to do so because we are comparing the errors of models against the same outcome variable, right? So the y is the same in all of these, and that lets me to do an apples to apples comparison of model mean squared errors. Okay, good. Any questions about this? So, oh yeah.
In this case, you're increasing the what's called the exponents.
Yeah.
And creating one more variables.
Yep.
But what if we have like a set amount of variables that we want to check?
Yeah.
How would this apply?
Yeah, so we'll talk about that, right? So that gets to model selection. So let's say you have like 10 variables, right? Well, which variables and in which combinations should we be putting in? Should we just put all 10 in? Well, if we put all 10 variables in, maybe I'm getting too much variance. I'm too much over here than over here, right? And so we're going to formalize how to do that. And to back up a little bit, this concept that I'm talking about here is going to be applied for much of the rest of the course. And essentially what we'll be talking about are different ways that we can add model complexity. One of which will be the selection of variables, but then there's going to be a whole bunch of other things that we're going to be doing as well. And it's all going to revolve around, okay, I'm teaching you about different ways to introduce model complexity, but you will fundamentally always go back to this concept here of balancing how complex I get in building that model based off of doing this testing of the MSE. Yeah.
And also here we're using the same x data set, just in different exponents.
Yeah. Yes. But okay, and that's like one way of introducing model complexity, and there will be other ways too. Yeah.
What distinguishes two explanatory variables from each other? Maybe I'm thinking about this too literally, but I see two variables, y and x.
Okay.
And like you're just doing different operations to x, but it's still coming from the same data. It's still x.
Yeah. So. It introduces degrees of freedom And let me see if I can, try and formalize how introducing the degrees of freedom gives you a lot more flexibility in the model output. Okay, so y, I don't know, A, B, C, D. So x is 1, 2, 3, 4, x squared, 1, 4, 9, 16, x cubed, 1, 8, what am I doing? Oh, yeah, other way, yes. 27, 4 cubed, 16 times 3, 48. Right? So, wait, yeah, I'm stupid, yes. That's, yes, 48, 16 times 3. No. You try lecturing and doing mental math. Okay. So y equals beta x, beta 1, beta 2. Actually, I'm not even going to do x cubed for a second. So look how much flexibility there is. Okay. So if I do beta 1, beta 2, y. Okay, if beta 1 is 1 and beta 2 is 0, right, then the set of points here would be 1, 2, 3, 4. And then 0, 1, 1, 10, 0, 100. The ability for you to reach a set of numbers here, if you only had access to beta 1, if you only had access to x, introducing x squared gives you a much larger range of possible outcomes, right? Does that?
If you say so.
Yeah.
I think technically you can fit any data set perfectly with the polynomial of the degree n plus 1, right? N minus 1.
Yeah. Some degree polynomial, but I guess the concept is like, yeah. Okay, so let's see here. There are some okay, maybe this is an easier way to show it, right? So if I had points on a line, then it is possible for me to intersect all of those points in a straight line with just one variable, right? Could I do it with 2 variables?
Yeah.
Right, because then I would just set my beta 2 to 0, right? Okay. So having one variable affords me some flexibility, but not a great deal of flexibility. Now, if I had data arranged in a parabolic shape, is it possible for me to intersect all of those points with a straight line? No, right? But I could with the parabola, right? So,
I understand how like adding higher degrees of order to a polynomial can better your fit. I just don't understand how like they become new explanatory variables.
yeah, don't get too hung up on the terminology, right? We think of explanatory variables as just like each entity is just something multiplied against a parameter, right? And it doesn't have to be. In this case, you have explanatory variables that are like heavily correlated or perfectly correlated, right, in some way. And you're going to find in real data sets, data is going to be correlated, but just because in slightly less ways, not maybe as strongly correlated. But just because they are correlated doesn't mean that they're all going to be considered one variable. Yeah. I think don't get too hung up on that, right? As long as you understand that adding more of these things, which we're calling adding more model complexity, affords you flexibility in the fit of your model. I think that's the more important takeaway.
Okay, sorry to slow things down.
It's all good. Okay, so what I had done in that plot as an example, we can try and actually formalize procedures to do that could actually apply to any model that you chose to test. Okay. And so that's what we're going to do right now. Okay. So how can we test the goodness of a model? And here we're talking really about, right, the test MSE. In other words, how well does our model predict against data that it wasn't trained on? And so we call this, as a generality, out of sample validation. Okay, so we have some set of training data. This is then used to calibrate the model. And then alongside a testing set of data, we then, let me write it first, test the model. And when we're testing the model, we need some metric by which we can understand how good a model is. And so we've talked about a bunch of these, right? So this might be R squared, standard error, R residuals, and then for me personally, right, really thinking about mean squared error. And then we take these metrics, we can go back to helping calibrate the model and kind of rinse and repeat. So this is the high level process with which we want to kind of approach doing this. And it's all about how well our model holds up when predicting against new sets of data. Okay. Okay, so one of the most common ways that we do out-of-sample validation is a procedure called cross-validation. So has anyone heard of cross-validation before? Yeah, a couple people. Great. So there's this question that's like, okay, I understand that we want to train the model against some data and then test the model against other data, but like where do we get a set of training data versus a set of testing data, right? And cross-validation is a way of leveraging a data set and breaking it apart into training and testing data where I, on average, am able to actually calibrate against the whole data set, but still test against out-of-sample data. And so how do you do that? How does that work? So cross-validation, use data to artificially make a test set. So in a k-fold cross-validation, this is a procedure that employs the entirety of your data set iteratively to test the predictability of your model on new data. So I'm going to give like a pseudo algorithm here to describe how to do this. Okay, so steps. 1, we define our k, and so this is known as the number of folds. So this parameter divides your data set into roughly equal parts. So a common k might be equal to 5 or maybe 10. Two, I split the data set randomly split the data set, randomly divide the data into k equally sized parts. And then for each fold, I will set aside one fold. So this is the test set. B, train the model on the remaining data. C, validate the model using the test set.
Are the folds and parts the same thing?
Yes. Record the performance metric. So this might be my MSE, AIC, BIC, etc. And for repeat step 3 for each of the K folds. And 5, aggregate performance metric. Across all K folds. Okay. Probably a lot to take in at once, but let's go through this. Suppose I have a data set. So this is my full data. Essentially, I'm going to take this full data set and carve out a piece here. So this then becomes my training data, and then I have test data. And I repeat this K times, right? So the idea is I have a big data set. I randomly assign it each row of the data 1 through K. And then I pull out, let's say, everything where the assigned number was 1, and then everything else is the training data. I run the regression against this data, and then I'm going to take the model that I've generated from this, and then calculate some performance metric, like a mean squared error on here. So this would be my out-of-sample mean squared error. And then I would put this back here, and I would take out a different slice of data, and I would do the same thing. And so if this was a 10-fold, then I would do it. This data would be divided 10 times, and I would repeat this process 10 times, and I would then have 10 mean squared errors, out-of-sample mean squared errors, and then you can average those to tell you about what the sort of performance of the particular model that you decided to make on this data was. Yeah.
Are there like any kind of rules on how big the K should be depending on the size of the data set?
No, not really. People mostly do like 3 to 10-ish, but you could actually go all the way. So there is actually, it's called leave one out cross-validation. That is a special case of K-fold cross-validation where K is equal to the amount of data that you have. And in that case, yeah, you would typically do that for like smaller data sets though.
Yeah.
And in that case, right, you would generate basically an error against one point, and then you're kind of like saying the average of all of those model fits against every single point in the data. Yeah. Yes?
So this process tests the quality of like the form of your model, not necessarily the model that is developed for each chunk of data.
Yes, that's right. So the whole idea is like, think of, let's say I had x1, x2, and x3 as my possible explanatory variables. And the question you might have is, well, if I run this model against just x1, or against just x2, or against just x3, or against x1 and x2, or against x2 and x3, or against x1 and x3, or against x1, x2, and x3, there are, wait, how many was that? 8, yeah, right. Was it 8? 1, 7? 7, there's 7.
Oh.
So you could do this process for all 7 of them. So every 7, let's say you did a 5-fold. So you would run 35 regression models, and you know, each one of those 7 would have 5 trained and tested models, and you would get the average MSEs, and then you could compare the out of sample mean squared errors of each of those 7 models against each other to see which combination of variables gives you the best out of sample predictions.
And pick the best model, run the regression again, and that's your fit.
Yeah, exactly.
Okay.
Yep. Yeah, and so that last step that was just mentioned about running it again, it's important to do that because technically speaking, you know, you want to train your model against the most data possible. So to kind of wrap up, once you've decided which one is best, you go back and just run it against the full data. Yeah.
But then how do we know if that new model really represents the full data?
Because you've done the cross-validation to
Just showing that process is valid.
Yeah, I mean, conceptually, what are you doing, right? You are saying, I'm running this model a bunch of times against data that I don't train the model on, and I'm basically choosing the one that gives me the best predictions, right? Yeah.
My question about, can I assume the model's performance will be better step by step when you repeat from the first to the second, third step, because the information has been, I mean, the full picture of your full data set, the full information of your full data set has been, the information of your full data has been step by step to these closer to your model. Because for example, at the first step, the model gets information, just the training data.
Yes.
A piece part of your full data.
Yes.
At the second step, you, randomly select some of the training data and also some of the information from the test data.
No. So it's exclusive. So if I were to, let me draw this in another way. So that's my full data, and I divide it into 4 pieces. Like this. So this would be a 4-fold, and in step 3 of my pseudo algorithm, I would do, let's say, train against these 3, test against the red, and leave that out. And then I would repeat, and I would do, let's say, these 3 and leave out the yellow. And then I would do these 3, leave out the green, and then these 3, leave out the blue. So every time that I do it, there's no overlap of testing data that leaks into the model training. I think, is that what you're asking?
Yes, maybe after class I can.
Okay, yeah. So one thing, if you kind of take a step back and think about this, is that the cross-validation process has nothing to do with the model form and structure, right? So this can be applied to any model, right? And in fact, this process is very commonly used, all the way from simple linear regression to, complicated neural networks, right? I can always loop back in and kind of do this to any model, yeah.
I have one question, I'm not sure if I understood that correctly. So you basically get like K different models, they're all like slightly different, right? And you choose the one that fits, like has the best like fit according to this, or do you like?
No. So that, when you go through the K folds for one particular model, that will tell you the average out of sample mean squared error, or like the average predictive ability of just that model. Now that mean squared error in itself is not meaningful unless I'm comparing it to other models. right? So the whole point of doing this is to test different models, because you may have a question of, if I have a model that includes all of these variables versus these variables, which one will predict better? That's the comparison that this will allow you to do. Or it could be, I have a model of this functional form versus a model of this functional form. Which ones do the better prediction? You do this process, right? Yeah, and so the way in which the types of things that we're going to be comparing are the things we will then be exploring for the rest of class, like what sorts of regression models are out there that let us do predictions for certain types of things. And if you ever have a question about whether or not the model that I learned about today versus next week versus at the end of class, if you want to know about which of those models predicts the best, you would still use the same procedure here, right? And so cross-validation is a very powerful tool to help you understand the relative predictability of different models. But unlike in R squared, right, this is like not a self-referential diagnostic device. The MSE on its own will not tell you anything useful. It has to be compared. I guess unless it's like 0, and then you're like, oh, there's no errors. But that would be highly unusual for real world data. Okay, any questions about that? Yeah, so I mean, given the importance of this particular concept, we're going to, let's see here. We're gonna do an application of this to model selection to the wages example that we looked at last time. And I'm going to walk through this manually to really kind of hammer this point home. It's one of these things that I really do want you guys to understand what's going on. And so, you know, we're gonna do this kind of by hand. And I think in the homework you guys might be expected to do something like that by hand. In practice, right, there are cross-validation procedures built into lots of functions and models that you can leverage. But given how important it is generally, for now, we're going to do it the long way. Okay, so we're going to bring in the data again. And I have a question about which of the following models better predicts wages. Okay, so one would be explanatory variables of height, sex, race, and education. And I want to see if that is a better or worse model than a model that has the explanatory variables of age, sex, race, and education. Okay? So let's build these functions ourselves. So I'm going to do this function called kfold.cv1. I'm going to have an input and then a number of folds. So the input So for the following function, input is the data and number of folds is RK. Okay? Okay, so if I want to split my data out into some arbitrary number of folds, can you guys help explain in English just procedurally how I might do this? Yeah.
Divide the number of rows by k. I mean, if we have a data set.
Okay. Yeah. So you're on the right track. So I want to take, but I want to split it randomly, right? So let's say I have 100 rows of data and I have like a k-fold of 5. I would want to somehow randomly break that data out into 5 parts. Okay. So the way that I'm going to do it is I'm going to, let's say I have 100 points of data, and let's say k is equal to 5 for now. Okay. What I'm going to do is I'm going to have the numbers 1 through 5 in a hat, and I'm going to say row 1 you get 3, row 2 you get 4, row 3 you get 2, and I'm going to assign randomly a number between 1 and 5 to each row. Does that make sense to everyone? So the way that I do that is I'm going to call that index. I'm going to sample 1 through, instead of 1 through 5 as the numbers in the hats, it's going to be numbers 1 through the number of folds. And how many times do I draw the number out of the hat?
Your length, your input?
Yes. So n row of inputs, or input.
N row instead of length.
Length is for a 1D vector, whereas the input is like a table, right? It's a 2D, it's a data frame. Yeah. And remember, we have to do replace equals true, right? Because if you don't do that, if I only have 5 numbers in the hat, but I have 100 data points, it's not going to work. Okay. So I now have a vector of numbers, 1 through the number of folds, that is a random assignment for each row. Yeah.
Does that make sure that each number, like from 1 to 5, is like has the same amount of?
It won't.
But isn't that necessary?
No.
No.
When you do it randomly, you'll get close, right?
Okay,
But
that's good.
like imagine that you had 101 data points. Does that mean you can't do a 5-fold validation?
Oh yeah.
Right. So doing the random draws will get you roughly close to an equal distribution.
Yeah.
Not always the same, but it's not really a problem per se when you're thinking about executing the k-fold, right? There's no step in which it requires an equal number of data points in each fold.
Oh.
Yeah. So input, so I'm just literally going to make a column called index, which is the assignment of the k-fold number, right? And so now every row of data is the same, except I've got an extra column which assigns you the fold. Okay? And then this is just a little kind of programming trick. I'm going to make a little, it's like a hold container. So this is the thing that's going to store the mean squared errors. Don't worry about this for now. We'll get back to it. Okay. So if you guys remember in the pseudocode, we had that step 3 where I execute this thing, and I'm going to do that a number of times. And how many times am I going to run a regression model in this procedure? K times, right? So I'm going to do for n in 1 through number of folds, which is our k. Okay. All right, so again, let's suppose our k is 5. I have all these data points that have randomly assigned 1 through 5. Now I want to generate my test set. How do I do that? I'll let you guys think about it. I know this won't be on the recording, but right, if I have, if my data is here, x1, x2, x3, x4, dot, 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 right? I've got this big table. And then here I have my index thing. And this is just my random values, 1, 3, 4, 2, 1, 5, 3, 1, 2, whatever, right? All the way down. Okay, this is the step I'm at now, and I've built this, and I've attached this column called index with this random assignment. Yeah.
I can filter the rows that have a certain index.
Yeah. So let's say now I want to build my test set. What I can do is I say, okay, from this data, pull out everything where the index is 1. That'll be my first test set. When I go back through the loop, I'll say, pull out everything that's 2. That'll be my next test set, right? And so on and so forth. Everyone understand? So I'm going through this loop, and I'm doing that, generating the training data, and I'm generating the testing data. Okay? Where the testing data is input, where input $index is equal to n. So that would mean my training data would be input where the column index is not equal to n. Okay, so basically what I've said is make the training data, or make the testing data everything where index is equal to 1. Make the training data everything where everything from the original input where the index is not equal to 1. And then I literally just run my model against the training data. So we're going to create something we'll call model.hold, and that'll be, right, our first one was earnings against height, sex, race, and education. Data is not our input, but our training data. Our predictions then are using the predict function, but remember you can put in a new set of data to predict against, and in this case that new data is our test set, exactly, testing.data. And then I can generate the mean squared errors from my predictions, which is the average of the actual data from our testing data minus the predictions squared, and then MSE okay, this final line, okay, so if you guys are following along so far, right, line 105 is our regression model, line 106 is running the regression model and predicting against the testing data, line 107 is doing the out-of-sample mean squared error, right? And so mean squared error is our actual y minus the predicted y. So our actual y from the testing data is testing data $earn, right, which is our y, minus our predictions, we square it, and then we take the average. Okay, great. So now for that means for k equals 1, I now have we'll call it the MSE of k equals 1. Okay, and if I loop back through, I will then generate k equals 2, MSE k equals 2. That's what's happening in line 107. The little trick that I'm doing, the little programming trick that I'm doing here is how do I store this mean squared error outside of the for loop? I made a container called mse.all. So when I first do it, mse.all contains nothing, right? And then once I go through the first loop, I redefine mse.all as the original mse.all, which is nothing, and that first MSE that I made. So when I go through the first time, suddenly that container will contain MSE k equals 1. And then when I loop through again, that container, which is MSE of k equals 1, will append on MSE k equals 2. So the second time I go through the for loop, now it's got MSE k equals 1 as well as MSE k equals 2, right? And that's the little trick that you can use in for loops to store the data on an outside thing. So it continues to append through all of them. And now I have a vector of my 5 mean squared errors. Okay? And that's the thing that I'm going to want to return. So return mse.all. So this will give me my 5 MSEs from my kfold function testing this model 1. And if I want to do another one for model 2, you can make this generic, obviously, but all I'm doing is I'm going to do a second one here. I copy and pasted the entire function, and all I'm doing is changing this height to age. Okay. Oops. Okay, so I run both of those. All right, so let's check it out. So kfold.cv1, is it wages or wage? Wages. And then what do you guys want to do? How many folds? 5. All right, we'll do 5 folds. Kfold.cv1, cv2, wages 5. Okay, so each of these are going to return a vector of out-of-sample mean squared errors that I can then compare to see which one does a better job at predicting. Okay. Let me do this. Model 1.mses and model 2.mses. Okay. So model 1.mses and right, and so you've got these numbers, they don't mean anything, right? There's nothing to compare against. And you've got these guys here. And you would want to take the average, right? So actually I would want to do mean model 1 dot here and mean model 1 dot MSE model 2. Okay? Great, so this has an average error of 759 million, whatever that means. This model has an error of 747 million, right? And so because on average, this model has lower mean squared errors of your out of sample, that isn't, right? That's basically telling us, well, if I used a model, so if I decided to use a model with the explanatories of age, sex, race, and education, that's gonna give me lower errors, better predictability than a model with height, sex, race, and education, right? Because this number is lower than this number. Yeah.
Without really having a good read on what the scale of those numbers mean, how can you like tell how much better one model would be to the other one? Like is like a whatever 500,000 difference significant in the difference of the predictability of the model?
Yeah. So you can that's something that is testable, right? And so you can imagine that some component of these mean squared errors actually has to do with even the randomness of the sampling of the data that I've done. And so if I were to repeat this many times, I would actually end up with a distribution of average MSEs, right? And so that would tell you kind of the spread of your predictive error. And so you could generate a distribution for this, and you could generate a distribution for this, and that would be an easy statistical test to see, well, it looks like those distributions overlap a lot, in which case I'd have a hard time arguing that this model is a lot better than the other model. But suppose those distributions were actually pretty far apart, you know, even though the numbers look close, right? Then you would say, well, this model always does better than the other one, right? And so, yeah, the mere fact that you are doing the folds part is actually giving you some information about the distribution of the MSEs. So if I were to look here, right, you can see that the MSEs are actually pretty wide, whereas here they're a little bit tighter. I don't know if that's just an artifact of the sampling that I did, so I'd want to probably try this a couple more times, right? But that may give you some, that may also give you some conclusions about like the dispersion of your predictions as well. Yeah. Yes.
So every time when you run the training data on like a specific, like run the linear regression model on the training data, it will generate a specific set of slopes and intercepts, right? So if you have 5 folds, there will be like 5 sets
Yes.
of slopes. And
Correct. Mm-hmm.
So this just helps us to pick which model, like which variables we want, and
Mhm.
then we need to go back to the full data set and run the.
Yep, exactly. So basically, you know, if I were confident, which looking at these numbers, maybe I'm not that confident, but if it were that it was always better and I'm like happy with this model, then exactly as you were saying, I would decide this model specification is the correct one. I would then take age, sex, race, education, run against the full data set to give me kind of the best estimates of the model. Yeah. Yes.
And that also works not just with multi-regression, but also if I just use a higher order of polynomial for one variable, right?
Yes. And we're gonna, yeah, so the class will kind of diverge a little bit because we do a little bit of training for both inference and causal investigation as well as predictive stuff. And when we start moving more towards the predictive stuff, we're gonna start looking at like nonlinear, non-parametric approaches. And so we'll build up the intuition there in the way that people have approached non-parametric models. And you know, the kind of first stepping stone is doing a bunch of like polynomial expansion models. Yeah, but that's like pretty crude, it's pretty bad. No one actually does that, right? But it'll give you the intuition to see why we do other things like splines and yeah. I think, yeah?
I was trying to follow along, but somehow my model when MSES, it says the training data is not time. Is that I'm missing a specific line or something?
Yeah, so I mean, what I have here in line 104 you might want to check 103 and 104. You might want to check that that's being done correctly, because if you have an error there, that'll break later. Yeah. If you can't work it out, either check the notes, because this code is going to get posted, or come to my office hours tomorrow morning. I think I saw someone with a hand. No. Yeah. So, you know, the framework for doing the k-fold, right? That's all spelled out in the code here. It's been specified to a particular model here, right? But it doesn't. But we can make it more generic, right? You could actually decide to put in the model as an input, and so. Yeah, and I think on the homework you guys will actually do that. So definitely make sure you guys understand this particular function. It's very relevant to a lot of the sort of diagnostics that we're going to do moving here on, especially in the like predictive space. Okay. Let's see here. Do we want to talk about confidence intervals right now? No, I don't. Okay, I think we're going to end slightly early today. Yeah, and if anyone has any other questions, I'll be here.